Seems all good to go. That's it. So hello, everybody. Welcome to our Quantum versus Astrophysics event. We have yeah, it might have been a bit of a clickbait to put that versus over promoted too much. Welcome, everyone. We have our panelists today. But before we get started, first of all, I want to thank you as well for being here with us. Otherwise, we'd like to acknowledge and pay respect to the traditional owners of the land, on which I have to probably tap that before we get started. So there we go. There you go. I'd like to acknowledge and pay respect to traditional owners of the land which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney is built. As we share our own knowledge, teaching, learning, and research practices within the university, may we also pay respect to knowledge embedded forever within the Aboriginal custodianship of the country. In fact, it is since their days, and perhaps ever since the first humans laid their eyes upon the skies and the world around us, from Copernicus to Galileo, from Madame Curie to Einstein, and many, many physicists, all of which have made crucial contributions to the human knowledge that what makes physics incredible has remained the same. It is our sense of curiosity and passion to learn about the world around us. No matter the specifics of the fields that we study, be it the mysteries of our cosmos, near and far, or the study of peculiar behavior of light and matter in small scales, what brings us all together is an itch for problem solving, and most importantly, a desire to gather around and discuss. And discuss is what we want to do today. Our panelists join us from two particular areas in physics, so astrophysics and quantum physics. So we shall begin with a short introduction of our speakers. We have Dr. Xanthi Krute with us. Xanthi was a Dickey Fellow originally at Princeton, where her research was focused on protected superconducting qubits. She completed her PhD at UCID before spending some time at Princeton, where she worked on scalable readout and coupling schemes of gallium arsenide-based spin qubits, and spent some time at UCID today. We have Dr. Sahan Mahmoodian with us. Sahan is a theoretical physicist researching many-body quantum optics under the ARC Future Fellowship at UCID, as well as being an associate investigator of EQUS. Sahan is interested in both the fundamental behavior of quantum optical systems, utilizing this for quantum technology purposes. He's also leading the quantum optics theory group here at UCID. Sahan has previously worked at the Niels Bohr Institute and the University of Copenhagen and the Institute of Theoretical Physics at Leibniz University, Hanover. On our astrophysics team, we have Professor Helen Johnston. Helen obtained her PhD at Caltech, followed by postdoctoral appointments at Utrecht University, the Anglo-Australian Observatory, and now the Eastern University, where she has a teaching position. Her research interests are the study of neutron stars and black holes, especially X-ray binary systems where the neutron star or black hole is accreting matter from a companion star. And finally, we have Master Covey Rose. Covey is currently an astrophysicist PhD candidate at the Sydney Institute for Astronomy, or SIFA. Covey's research is focused on observational radio astronomy, especially dwarf stars, as well as identification and analysis of radio emission from high-energy astronomical transients like supernovas, flaring stars, and more. As well as being a Veritasium producer, he's the founder of a publisher of Fun Fact Science, a page designed for education and science communication, or as a co-host of the Space Case Sarah show on IROC Space Radio. That's a bit detailed. So if we could get a round of applause for our speakers today, that'd be great. Beautiful. So maybe we'll get started with the, I've obviously tried my introduction as well, but we talk about yourselves as well. So maybe you start from the left there. Tell us about yourself, your field. How did you become interested in perhaps what you do today, and what was the path that you kind of paved until being in this position right now?
Oh, okay. It's a lot of questions. So first of all, yeah, thanks for inviting me, Faisak. And it's a very good turnout, better than some of the lectures. Maybe just my lectures. Yeah, so how did I get interested? So I actually did my undergraduate here at the University of Sydney. And I quite enjoyed the optics course in third year. So that was taught by Martijn, and I think it's still taught by Martijn. Yeah. So that's how I got interested in optics. And so then I did my PhD also here at the University of Sydney in optics. And that was more on the side of photonics and photonic nanostructures and trying to understand how to model them and why they behave the way they behave. But then I decided to change my field for my postdoc. So I got a grant to go to the Niels Bohr Institute. And so I think in science research, it's always nice to, if you're kind of moving from one part of your career to another, you try to choose some area of research that has a good overlap with what you know, but also has some new stuff. So I moved at the Niels Bohr Institute, the research group was doing quantum photonics. So some of the theory in quantum photonics and classical photonics is the same. So you need to know the classical properties of your photonic system to be able to know how it behaves in the quantum realm. But some of the theory is totally different. Quantum optics, as some of you may know, you have to use quantized fields and wave functions, and that's quite a lot different to classical photonics, where you just usually are interested in classical Maxwell's equations. So that's how I went to quantum photonics, and I've kind of stayed in a similar area, quantum many-body physics, or in the introduction, did you say quantum many-body physics?
That's right.
Yeah, so you already said that. So quantum many-body physics just means dealing with quantum, in my case, quantum optics, where you have lots of photons and or lots of atoms. And theoretically, that's very challenging. So there's some new things to learn in this area. And in terms of applications, that has applications in quantum computing and other areas of quantum technologies. And so what were some of the other things? How did I get interested?
Yeah, for sure.
So kind of just doing something I'm interested in and then moving on to something else I found interesting.
Kind of like moving on from undergrads.
Yeah.
Following the passion.
Yeah.
Awesome.
Thing. Yeah, just being curious and moving on to the next interesting thing. I don't know if that's excellent career advice, but I think in terms of enjoying science, I've enjoyed it following this path. So
go with Santi.
I feel like my trajectory is quite similar to yours. In that I also did my undergrad here. And then I did my PhD here in David Riley's group, the Quantum Nanoscience group. There is one small difference. I was studying, I wanted to be a lawyer. And so if you do law here, you have to do, I don't know if you still have to do this, but you have to do another degree with your law. And I always loved science. I was like, I'll just do science. And in third year, I did, actually, I think I might have done the optics course, but I did the condensed matter course and really loved it. And at the time, David Riley was teaching it. And he basically, I was thinking about doing honors and he was quite persuasive that I should come and do honors in his group. And I was like, all right, I'll just take 1 year off, do honors, and then I'll go right back to law and get back on track. Then finished honors, and I would like to think I decided to do a PhD. He was also quite persuasive in terms of the benefits of doing a PhD. So I had a friend who was also in the same position. She was studying law as well, and we were both in David's group, and we both fought the university to allow us to go back to law at the end of our PhDs. So it was just don't know what we were thinking. Quite the fight, and neither of us went back to law at the end of our PhD. The university eventually agreed that that would be okay. So I was kind of a reluctant physicist. Like even when I was doing my PhD, I was like, I'm going to be a lawyer. So I did my PhD in experimental quantum computing. And so there are many different ways to build a quantum computer. And I've worked in 2 of them. The first one I did my PhD in was encoding quantum information in the spins of electrons. And so it turns out that semiconductors, or very special types of semiconductors, have the property that you can trap single electrons and kind of really carefully control where those electrons are, put on a big field to define some spin splitting, and you can use those states as basically quantum transistors. And so I did my PhD in semiconducting qubits. At the end of my PhD, didn't really know what I wanted to do. I got an email from a professor at Princeton who my supervisor knew. So unfortunately, sometimes how these things happen is your supervisors know people and you make connections through that, saying you should apply for this fellowship at Princeton, and it's due in 2 days. So I wrote a big research, you had to write a research proposal and do all this other thing. So I stopped what I was doing, wrote this proposal, interviewed in his lab and a bunch of other labs. I was like, well, I'm over there, I might as well go visit a few labs. But I got that fellowship and it was fairly hard to turn down. So I finally decided, all right, probably won't be a lawyer. Do my postdoc instead. And so I did that. That was, as Sahan said, it kind of built on a little bit of what I knew from spin qubits, but incorporated superconducting circuits. And in particular, you can trap light in superconducting circuits or photons. And so what I was doing is using these superconducting circuits to, or the light that you can trap in these circuits to mediate really long range interactions between single electron spins. By long, I mean like a couple of millimeters. But that's a lot longer than the couple of nanometers that typically these things interact over. So then I kind of joined another group after that at Princeton, kind of working my way from pure semiconducting qubits to pure superconducting qubits. And so that's just where you use not just the fact that you can encode, that you can trap light in superconducting circuits, but you can also trap other types of excitations that you can use for quantum computing. And so that's where I kind of landed. And then after that, I came back here where I'm currently setting up a lab to work in similar things.
Awesome. Thank you.
That's what we call a victory when we steal students from law. So yet again, number 3, I did my undergraduate degree here. Did you? Oh. We don't have a complete set. Anyway, I did not, however, do my PhD here. I went overseas to do my PhD, something I would heartily recommend. Very good idea. So I went to Caltech to do my PhD, and I like to say that Caltech is a great place to have been at. Very high pressure place, wonderful place in many ways, but wouldn't want to spend my whole career there, if you know what I mean. Anyway, I had a great time, learning the ins and outs of astronomy, because of course Caltech runs the 5-meter Palomar telescope, privately, and so you get all this wonderful telescope time. So yeah, a great thing there. As Xanthi says, the next stage is often very dependent on who you know. Towards the end of my PhD, I was having lunch with a visiting guy from Holland, friend of my supervisor, and we were just, he said, why don't we go have lunch together? And I was sitting having a chat to him, and about 3/4 of the way through it, I thought, oh, this is a job interview, isn't it? So sure enough, I went and did a postdoc in Holland with him, not having realized I was doing a job interview, which I have to say is the best way to do a job interview. You don't get nearly as nervous. Anyway, so postdoc in Holland, again, learning a whole new bunch of skills, because I moved into X-ray astronomy, which I hadn't seen before. You just sort of build your skills as you go along. Came back to Australia to work at the Anglo-Australian Observatory, back to my real love, which is optical astronomy, and then went through a sort of series of postdocs here at Sydney University, working on all sorts of different projects, until eventually I landed a teaching position, which stopped me doing astronomy. Oh, well. But yeah, as I say, over those, out of all of that, I've my passion is these binary stars. In terms of how I got into astronomy, I've always known I wanted to be an astronomer. I'm told at the age of 6, I announced I was going to be a paleontologist. And then at the age of 7, I decided I was going to be an astronomer. No clue where it came from. Just I did, and just never changed my mind. So having said that, I will say I also know many astronomers who didn't decide they were going to do astronomy till after they finished their undergraduate degree. So, and they are at least as good at astronomy as I am. So there is no correlation, if you know what I mean. It just happens that some people decide early and some people don't. And it's doesn't appear to make any difference whatsoever.
So,
I feel kind of left out that I'm the only one who didn't do it. I did my undergrad in Jerusalem at the Hebrew University of Jerusalem. Whole long story as to how I ended up on that side of the world. But yeah, would not recommend doing undergrad in a foreign language. Not fun. I did actually also want to be a lawyer. I had, before I moved to Israel, planned on, and I was accepted into an arts law program in Melbourne where I grew up. So yeah, I'm surprised to hear there are other lawyers, almost lawyers. Yeah, so I don't know how I just developed this passion for space, and I decided, even though I didn't have a strong science background, wanted to do astronomy. The institute I was at only offered physics, so did all of the fun physics and math courses that are super relevant to my career and life as an astrophysics person. Trying to remember the other questions. There were so many.
yeah, I think that's pretty much the path that got you to where you are at the moment, or
Yeah.
what's relevant to
Oh,
studies.
I like in a research sense, because I didn't have a strong science background or math background, I felt like I was slogging through a lot of the undergraduate coursework. And I just wanted to find somebody who was a researcher in astrophysics who I could kind of latch onto to have that almost escape, when I had the time for my coursework. And I went away to a weekend retreat that was focused on astro. There was a researcher there who was working on radio astronomy, and that's how I ended up on radio astronomy. That
Amazing.
could have been in any part of astro and had just as much of an interest and passion. And yeah, kind of like what you were saying before about changing topics, I guess I changed slightly. So throughout undergrad, I was working on supernovae within the framework of radio astronomy. And now I work on like dwarf stars that produce radio emission and galactic objects. I mean, it's interesting you were talking about things that were relatively far. Yeah, millimeters. I mean, I went from undergrad to now to working from megaparsecs to parsecs. Like, oh, the star is really far away. Light years. And yeah, it was actually quite a fluke that I also, not quite a job interview, but so I work in Tara Murphy's research team, and I had only met Tara because she had come to Israel for collaboration with my undergraduate supervisor. And I was showing the Australians around, which kind of felt weird being an Australian in Israel. And like, wait, are you with us? Are you in the visiting group? And yeah, when I decided that I was, continuing and doing a PhD and I wanted to explore my options, having done a summer project at Caltech, I know exactly what you mean. So I decided against Caltech in the end and just emailed Tara and said, I want to do a PhD in Australia. Will you have me? Kind of thing. And yeah, went from there.
Amazing. It's very interesting to hear all these kind of similar but yet different stories, how everyone's kind of made their path to this, what they are today. I'd like to just announce that probably want to make a theme out of today's talk. I think, as you mentioned earlier as well, something that we want to kind of gain some sort of understanding about what it is on a day-to-day basis to be a scientist first of all, and then a physicist at your specific role. And so I want to make it a little bit more philosophical, maybe. What do you personally think a scientist is, or a physicist is? What skills or attributes does a good, quote-unquote, physicist or science staff, anyone who'd like to jump on that?
Bypass the first part of the question. The second part.
Sure, absolutely.
So I think that one, there's like, okay, good at the classroom things and the exams and whatever. There's that part. I also think that in practice for real world scientists, one of the most important skills that I think you can have is resilience. I think that when you're doing research, it's not necessarily the same thing as someone setting you an assignment or an exam that has, well-defined answers if they've set the exam right. And so when you're doing open-ended research, sometimes you get on a roll and you have really great results and everything is working. Other times you encounter problems that, your supervisor might be able to guide you, but you don't actually know, they don't know the answer to, they don't know the exact solution, and you're trying things. And so I think that one of the most important qualities that researchers can have is, I guess, a resilience, which can come from like an enthusiasm and a love for the actual subject. Sometimes it's just pure grit and determination to keep pushing through. Yeah, but I think that's a really important skill as a scientist to have.
Yeah, sounds great.
One thing I think that's quite important in doing research is asking the right questions. So when you're in undergraduate, usually you're given questions by your lecturer or whoever. But as a researcher, you have to ask the questions yourself and solve the questions. So and you have to be quite judicious in what questions you ask, because it takes a lot of time to solve questions. And solving the important questions first is best, I guess. And that's how you make big research breakthroughs. So that's important. In terms of research style and personality, I guess there's room for different kinds of approaches. Someone who's like really focused and just wants to attack, is just concentrating on one area, that's very good. If you want to choose a very difficult and challenging but very important problem, you can work on that. But if you also have a mind that's like constantly wandering and gets interested by different things all the time, you know, sometimes happens to me, that's also not always bad, because you can have interests in different fields and pick up knowledge in different areas. And that's also how you become a good physicist and make impact by, you know, realizing that there's something related in this field that field is doing, and you kind of can bring those together. So there's different personalities and different skills that make a good physicist. And yeah, so there's room for different kinds of people.
Sure. Yep.
Yeah, I mean, I guess I would definitely echo that, both those comments. Resilience is a really big one, because especially when you're starting out, yes, there's this great article that I like to point students to, which is basically that when you're doing research, you're confused all the time. I mean, by definition, if you knew what you were doing, it wouldn't be research. And you have to realize that that's what your life is going to be if you're doing research, if you understand. And it can be really dispiriting, especially when you're starting, just knowing, you know, I'm 3 years into a PhD that I'm supposed to finish in a year. I still don't know what I'm doing. You know what I mean? A lot of students really struggle with this sort of problem. And the only thing that can get you through is, you know, well, everyone feels like this. You know what I mean? And in the end, you write your thesis, and it's probably never quite as good as you thought it should be, or covered quite as much as you should have done, but it's yours, you know what I mean? And you can be proud of it. And in some ways, all of research is like that. You know, yeah, you have this fabulous data set. You know, as an astronomer, that's the way I think, if you know what I mean, that you're sure you go and take this wonderful data that's going to really, really nail that problem, and it just kind of doesn't. You know, sometimes it's through no fault of your own because you've got bad weather. Other times it just turned out that problem wasn't solvable with the tools at hand. And it's like, yeah, you just got to pick yourself up and keep going. I mean, you know, the way science is structured, you can usually get a paper out of it, you know, but it's not quite the world-shattering discovery you were hoping for. But that's just, yeah, the way that life goes. But I would certainly agree with the idea that different approaches, there's room for all sorts of different approaches. I didn't know when I started that actually what I'm really good at is just detail work. I love the whole procedure of data reduction and observing and just being careful. And yeah, if you'd asked me, you know, when I was 15, of course I want to be a theoretical physicist. Everyone wants to be a theoretical physicist, right? It's like, well, no, actually, that wasn't my particular thing, you know. That's not the way my brain works. But turns out physics is big enough for all of us. So yeah, more will come up, I'm sure.
Cool.
Yeah, I feel like it's cliche to say I definitely agree with everything that's been said, but I kind of do. I think what I would add is specifically to the point that Xanthi raised about resilience, and also in terms of like doing your own thing and finding what works for you. I think that the most important thing is finding a a productivity level. This might sound silly, but a productivity level that suits you, right? Because like like you mentioned, like it's not a set question and a clearly defined time period. Like it can go on forever. You have to define what an individual project is. You have to define for yourself what your deadlines are. And exactly, there is no end. And I feel like we're all here because we're passionate about learning more about our fields, and it can be a slippery slope of just getting dragged into doing all of the work, like work at 110% of productivity all the time. But the problem is, if you do that, you will burn out and you will find yourself in an unhappy place. So I think it's kind of like there's that cliche of research is a marathon, it's not a sprint. And there are some people who say, yeah, but you have to like sprint in a marathon to be an Olympic marathon runner. Yeah, maybe, but it's not healthy. And I think the best thing that you can do for yourself to maximize your resilience is to find a topic that you love and a pace that you can work at that topic consistently, so that you don't grow to hate it eventually.
Yeah, especially on that topic, I feel like that's a question we'll come back to. Something I want to know about good and bad aspects of research so far, at least, because I think a lot of people outside of research see the output, basically, what superficial that comes out in the end, but they don't see the processes that goes through. So perhaps there's some of the negative sides and the positive sides that we'll come back to it. But beforehand, just to know more about the topics, I want to know, and as you mentioned, Helen, as well, about the broader questions and the bigger questions in the picture. What do you think, well, are the broader and those big questions in each field, in quantum mechanics, obviously, and astrophysics, that you would personally like to have answered and potentially answer yourself? So we can start from each side. Who's interested to go first? Yeah, we can start from or perhaps introduce us to the question that is basically being explored at the moment. Not necessarily by yourself, but a big question.
I can go if you want. If you want, mine is easy because I spend a lot of time working on quantum computing, and so that's a very kind of I don't want to say well-defined goal, but it kind of is. It's like we know what we're trying to build. There's a lot of physics, a lot of quantum physics that goes into it. There's also a lot of engineering, and so it's a kind of for people who like both the kind of engineering side of things and, with not peppered, it's more than peppered, but, thrown in with a lot of quantum physics, it's a really enjoyable field. So in my field, what people are trying to do is a couple of things. What we really want to do is build a large-scale quantum computer which can perform particular algorithms that can only be performed on a quantum computer that have, useful benefits for humanity. And so there's a few challenges. One of those challenges that I spend a lot of time thinking about is when you encode quantum information in a spin or a superconducting circuit or an ion, it's kind of fragile. It doesn't live forever, and it's quite sensitive to noise in its environment. And so qubits will live, bad qubits tend to live for a couple of nanoseconds. Kind of really good qubits might live for a millisecond or so, a bit longer. But it's kind of, and these times are really like, there's a time associated with a quantum system decaying or dephasing. But if you're a computer scientist, that kind of translates into an error rate of your quantum computer. And so one of the big challenges for us is bringing down the error rate of this kind of large qubit system such that we can correct it and do actually useful things with the quantum computer. There are other, depending on the platform, there are other challenges. We'll probably talk a little bit more about this later. Every experiment I do needs to happen at a fraction of a degree above absolute zero. And so when you start envisaging putting many millions of qubits in one of these big cryogenic pieces of experimental equipment, and sending down all the kind of controls that you need from room temperature. Actually keeping that system cold is a challenge. And so there are many engineering challenges associated with quantum computing, as well as kind of fundamental physics and computer science issues. And those are I think the big questions that I spend a lot of my time thinking about.
Cool.
Yeah, so in the area of quantum optics, I also have some interest in quantum computing, and so there's approaches for building or suggestions for building a quantum computer based on optical photons, and it's not clear yet what the best way to produce these photons is. So one needs to produce these photons such that they have very low noise. Noise is very important in quantum computing. You want this to be as low as possible. So there are error correction schemes, but they have noise thresholds, and you need to be below this threshold. So one of the questions that's like maybe you could call it a big question that that's related to my research is, can we use quantum emitters, so solid state quantum emitters, to emit photons that are below this noise threshold? So that's kind of a big question, because then you could use these solid state emitters that emit photons very rapidly to try to build a quantum computer with them. So there's a company called PsiQuantum. I don't know if you've heard of that. And one of the things, the thing they're trying to do is to build a quantum computer based on photons, but their sources are not these solid state things. They want to use these probabilistic sources. Yeah, I mean, if you're interested, I can tell you a little bit about that later. So that's kind of a big scientific question. Yeah, quantum computing has a lot of big questions, both in physics and in computer science. And then there's kind of little big questions that I'm kind of interested in. So like some of the stuff I'm doing is also like, if you have an ensemble of cold atoms, so many cold atoms, and you shoot a laser at it, can you write down a good approximation for the wave function of the photons that come out? So these atomic ensembles, people have been doing experiments with them in quantum optics experiments for, a couple of decades. But this problem at the many body limit, no one knows how to really solve that. So that's kind of that doesn't have huge applications, but it's like one of the small big questions, if you like, that I'm interested in.
Cool.
Well, if we're going big as an astronomer, I can go much bigger than you. I tell you that one of the really big things that I think is coming in astronomy is big astronomy. One of the big problems we have, sorry, I keep using that word big. Anyway, one of the problems we have in astronomy is there's too much out there. So there's so much we don't know. A supernova goes off. What we really need to know is, what was it like before it exploded? And we have no idea, because nobody knew it was going to explode. So nobody had looked at that star. So supernova 1987A, we learned more about that from that one supernova than from, practically anything else. But we have no idea what kind of star it was before it exploded, because literally it had appeared in a catalogue, and that was it. So I'm really looking forward to this new coming era where we've got these huge telescopes that are going to be surveying the sky night after night. And so if anything unusual happens, when the next supernova goes off, we're going to be able to go back through history and find the image, the spectrum of that star before it happened. And things we don't know we need to look for are going to be there because we looked at everything. That's going to be exciting. And that's the sort of thing that couldn't happen until really recently, because we just didn't have the computing power, we didn't have the storage capacity, and these things are only going to get better, possibly due to our friends over here in quantum. That's going to really change astronomy when we can do things like that.
Really?
Yeah, I completely agree with that. And just for you to have an idea, so one telescope that I work with, a radio telescope in Western Australia called ASCAP, I believe the throughput of the data going through ASCAP on a daily basis is comparable to the data throughput of all of Australia's internet. I might be getting that number slightly wrong, but
it's something ridiculous.
Yeah, something kind of like that. So it's a huge problem for all astronomers. I also definitely relate to what Helen said about trying to understand the history of the star. I guess in a nutshell, like the big question that I've been focused on for all of these different subtopics that I've worked on has been kind of how stars live, how stars die, and then also how stars live after they die. Because there are these zombie stars called neutron stars that do a lot of very interesting things after the supernova, after the star has died. And so a lot of the work that we do is kind of comparable to like CSI work. So a star explodes, supernova, and we use radio observations to see how the shock wave of that explosion is propagating out through space. But the stuff that it's hitting in space, which is causing the radio emission, is all the stuff that the star was kind of like throwing off in tantrums in the years before it exploded. So you can kind of work backwards and understand what the death of the star was like by seeing the shockwave afterwards. And so, yeah, I think just like to be able to predict it and to know in advance when a supernova is going to happen, to understand just completely the life cycle of a star would be huge on all scales.
Yeah, it's interesting.
For the wavelengths of centimeters.
Yeah, with all that is different in terms of theory, I feel like it's interesting how similar the approaches are to big questions. I feel like there's a big theme in all of science probably about making accurate predictions, right? So that's a lot of the point of understanding a system from a certain amount of time and see how it evolves, especially in quantum mechanics. That's definitely a topic of discussion. Something that I would perhaps want to focus on afterwards, and I think it was thrown around as well, which is amazing to see, is although the theories again are so different, how do you think potentially these fields can communicate with each other? Do you think, well, has it actually been, do you have an experience of doing a project where quantum physics has been collaborating with astrophysics, or projects that are happening at the moment you're aware of that's happening? And how is that actually usually happening? So I was trying to think of projects in that regard. So like breakthrough starshot or light sails, that's potentially something that's a topic of discussion, but yeah, perhaps.
Like just like stars, our understanding of stars wouldn't work without quantum. Like it wouldn't make sense. The nuclear fusion that drives like the life of the star wouldn't work without some like fundamental quantum physics. I think that definitely what Helen mentioned before about having quantum computing to do like the processing and management of the data that we're getting, which is so phenomenal, is a huge thing. And I would love to see more kind of combined projects between people who work in engineering and computer science and these fields with astronomy.
Well, as you say, I mean, everything we do in astronomy is based on quantum physics. I mean, our detectors, you know, those photons, right? They hit our CCD detectors. They make they allow us to detect light. You know, as I say, you know, it underpins everything. But I have to say, it's kind of old school quantum. Do you know what I mean? It's like the quantum physics that we use has been been around for a while. The only experience I've had of an overlap with current quantum thing was back when I was a postdoc. There was talk of developing a superconducting tunnel something or other as the universal detector in astronomy, where you could detect everything from gamma rays all the way down to radio waves. And they were working with quantum physicists to do that. I don't know what happened to the project. So that was possibly not a very successful collaboration. But yeah, as I say, sorry, I'm drawing a blank on the actual collaboration.
This I guess maybe doesn't so much pertain to research output, but certainly in cryogenic experimental quantum physics, we borrow a lot from things that NASA learned. Deep space is very cold and also high vacuum, and we operate in environments that are very cold and very high vacuum. In fact, we are colder than deep space by quite a lot. And so things like, and I feel like this is a David Riley story, that I feel like if it's not true, blame it on him, because I think he told me. So inside our cryogenic apparatus, you have your, fragile quantum computer right at the bottom of this big cryogenic piece of equipment, and it's at about 10 millikelvin. And the rest of your fridge is there basically to get that tiny little part cold. And so things like radiation shielding on the lunar modules, they have these layers of aluminium and then a kind of mesh, and then aluminium and then mesh. And many layers of that is extremely good at keeping photons out that might heat up the system. And that's exactly what we find in the inside of dilution fridges, is kind of very similar wrapping to what they wrapped spacecraft in, and I imagine it's in telescopes as well. We also care a lot about thermal budgets and I guess rates of thermal expansion. If you make something and you make a whole bunch of parts and you want them really firmly bolted to each other, and they're fine at room temperature, but then you cool them down, they're not necessarily going to be firmly bolted to each other. And so I regularly find myself consulting, JPL tables of thermal expansion coefficients, because no one else really bothers to characterize all the different thermal expansion coefficients and thermal conductivities of all the different types of copper and purities of copper, except NASA. And so from the experimental perspective, we certainly borrow from the I don't know that NASA really is spacecraft, which I'm going to loosely extend to astrophysics and telescopes.
Well, I'm working currently on a project that has some people in astronomy involved. So these days, machine learning is used everywhere, and it's used quite a lot, as far as I understand, in astronomy. So people, I think, like Tim Bedding, they look at oscillating stars and they look at the light coming in, and it has some sort of time trace. And they look at this light and they want to say, does this belong to star category A or star category B, right? And that's a machine learning problem. And so what can quantum tell us about machine learning? Well, quite a bit, actually. So there's some similarities. So if you think of quantum many-body wave function, so imagine I have a whole bunch of spins. They can be spin up or spin down. So one spin can be in a superposition state, up plus down with some coefficients. Two spins, up plus up down plus down up plus down down. So there's 4. And if you go to many spins, the number of basically that space grows exponentially. So it's hard to write down a quantum many-body wave function because you have to store or write down an exponential number of coefficients. And if you think about machine learning, the space you're working in is also exponentially large. So imagine pixels on a screen, they can be black or white. So if you have 1 pixel, it's black or white. And then 2 pixels, you can have black, black, you can have black, white, white, black, or white, white. So the phase space of that problem also grows exponentially. So in quantum mechanics, people have come up with clever ways to not store this huge exponential, to deal with this huge exponential phase space, but to deal with some section of it, which has all the useful information, and just neglect the rest. And then you can come up with schemes that grow polynomially with the number of particles and make it computationally efficient. So the project that I'm looking at is adapting those schemes to see if we can do this in machine learning for time signals, and that's useful for astronomy.
Perfect. So I'll probably phrase that for you against hand. How does the collaboration occur? Is it any different to perhaps two quantum physicists working with each other or two astrophysicists working with each other? What's a process of two basically people from two different fields getting together and collaborating?
So that one I can't really comment on so much because I started this with someone who's in complex systems, so Ben Fulcher. So I said like, this approach might be useful for machine learning. And he said, I'm already working with astro people and so on. So it's an indirect, so it's kind of an indirect collaboration.
Yeah.
But, yeah.
Cool. I think, yeah, absolutely. Yeah, for sure.
Not like it's kind of a improper answer, but the best way to get those collaborations going is just to get out there and meet people, talk to people. like I hate seeing groups of people from their own research groups in the tea room or having lunch just with themselves rather than actually sitting with other people and kind of having a more open circle. Going to conferences is another great way to meet people who are working on different things and kind of getting ideas when you speak to them of, oh, wow, they're doing that thing that I never thought was relevant to my work, but maybe it is. So yeah, that would be my best.
A lot of which is probably now happening on Zoom as well, or online meetings.
I mean, not necessarily. I just got back from the US and I was at a machine learning workshop that was specifically for Astro, but from all different parts of Astro. And so, yeah, machine learning was also not something that I ever thought would be relevant to my work. And yet, yeah, so yeah, in person is, I think, ideal where possible. But yeah, any sort of collaboration. It's also something that I get from, so you mentioned in the introduction, I do a bit of science communication work online. And I've connected with so many wonderful people who work in astro or physics or totally different parts of science or not science. And by collaborating on science communication, I've ended up learning about other areas of science. I have a friend who worked in ecology with owl migration and hunting patterns using GPS tracking. And there was like a whole weird moment that we shared some insights into how he does that tracking and how that could be relevant to work that I do. Yeah, so just.
And can I just bring this back to the earlier discussion about weird ways to get jobs and PhD things and that? It's never too early to start just making connections and chatting to people. And, you know, if there's an opportunity to go to lunch with a visiting speaker, just do it. You never know when later you'll be able to just go, hi, I met you in Sydney, and I'm looking for somewhere to do a PhD or something. Yeah, seriously. People, it's all about people.
And I think just as maybe a caveat to that, I know that like not everybody is necessarily an extrovert, and I consider myself somewhat of an extroverted introvert. Like my base state, my ground state, like Netflix on the couch with my dog. That's it. No people around. But and my partner, of course. Dog first. But something that was, so when I was at Caltech, my summer collaboration, I felt very awkward. Like my peak awkwardness was there and not feeling like I could speak to any of the other people there. And the senior student who was supervising me said, this is Caltech, everybody's awkward. Keep that in mind. If you don't feel like you have the guts to necessarily like take this advice and start talking to people at conferences or at lunch, just do it. Like we're all a bit awkward. It's
we're all physicists.
That's actually a point I was going to expand on later as well. What are some suggestions? No, definitely not the awkward part. Yes, I completely hurt myself how it sounded. But how do you think there's some methods for undergrad students? I feel like there's more opportunities for postgrad students to get involved in networking. I personally think, you know, a lot of what we learn at university you can find online and online resources as well. The point of university is kind of network with different people. So what do you think there's some ways, or at least kind of like a template pathway for a lot of students undergrad to do that networking with people researching?
Well, I'm obliged to say that as the person who manages the SSP, doing SSP projects is an excellent way to start out because the sort of interaction you get doing a project with a researcher is so different to what you get with a lecturer. I mean, there's just no other way about it. Very often. And so again, if you're doing a project, go to the group meetings, because that way you meet all the other, particularly the other junior researchers, and you can just get chatting and find out what they know and you know where they go and so on. Take the opportunities if you ever get them to go to a conference, or you know go on a an observing trip, or whatever the equivalent is if you're a solid state physicist or whatever. And again, you know, was always the introverted type, and you know wouldn't have done that by choice, but you don't regret it later. It's the way to to start.
Cool. Yeah. Have any inputs on that otherwise? Cool.
No.
So next thing we was going to talk about is a lot of what we see as an insight into the life of a physicist is through films. And I don't think films depict that quite well. So, I mean, for example, Oppenheimer was out a few months ago, and you can...
Oh, look,
oh, wow.
We've been timed out.
I'll fix that for you.
This is the line.
It's really on theme. Perfect. Yeah. So I feel like a lot of what's depicted, especially with the background music, sounds very different to what it could potentially be like. So we would appreciate some insight into what really day-to-day life of a scientist or physicist actually in this case looks like.
I mean, maybe like the one depiction that I most related to was the opening scene of Don't Look Up. Like, sitting there listening to Wu-Tang Clan while coding, like that is, I feel like most of my life. I was kind of going on before about like healthy routines and productivity, and I try to just like keep a healthy routine and then, you know, get to the office, allow myself to check emails, and then choose whatever thing I feel comfortable to work on. So I generally have, my Google Calendar is a scary place, and I color code everything, and I plan to be hyper productive, and I never end up being hyper productive. But I generally will, you know, switch tasks every few hours, try to work on different things, try to recognize where my energy level is at and where my mindset is at. And if that is reading through papers and trying to get insights, or if that's writing code, or just having chats, I find like just sitting down with other people in my research group or in different research groups, and having a face-to-face conversation can be super insightful. So yeah, most of my time is talking to people, reading papers, coding, Googling how to do the coding.
Yeah, and coming from a slightly different angle, as an observational astronomer, you might think I spend all my time looking, or at least like when I was, you know, doing this full time looking through telescopes. Well, first off, you don't look through telescopes; they don't have eyepieces on them. But even going to the telescope is actually quite a rare event in the life of an observational astronomer, because as an observer, at my best, I might have spent 2 weeks a year, tops, actually at a telescope. And you collect enough data in that time to keep you busy for the rest of the year. The rest of the year, we call it data reduction for a reason. You come back with you know, gigabytes of raw data, and you bring it down to, if you're lucky, you know, 100 numbers. So basically, yeah, you throw away all the stuff you don't need. You do all the analysis, and you get the actual bit of science out of it, which was a very small amount. The first guy I ever did a project with used to joke that he used a $10 million telescope. This was a while ago, and he sent the light through a $10,000 spectrograph, and then he put the thing on a screen and measured the one number he wanted, which was a redshift, with a 10-cent plastic ruler. So that's the real data reduction, if you know what I mean. But the point is, without all that first stuff, the $10 million computer and that, you can't get the redshift. But yes, most of our life is not spent at a telescope; it's spent in front of a computer. As you say, banging our heads against code we don't understand or whatever. So in my case, I have the long-lived problem, which is all the software that I know and love has all gradually become obsolete. and so yes, I'm sort of, you know, hanging out with my fingernails. No, don't. Yes. So, yes. One of these days I have to retool and learn all.
And now in terms of quantum physics, what do you think is similar? What's different? And obviously your insight about it.
Oh, well, I'm an experimentalist. And so I do not spend, well, actually, at the moment, I physically spend all my time sitting in front of a computer. But when you're doing your PhD and your postdoc, that is not what you do. So experimental physics and condensed matter experimental physics is really hands-on. So you are in the lab working with cryogenic apparatus, you're maintaining it, you're making sure it's running smoothly, you're making sure you're not like, you know, sending too high power pulses into your fridge and heating up, and you're working with liquefied gas. And so you're making sure that's not getting too hot and sending things, you know, to very high pressures. You are building parts for your fridge. You are writing code to control your experiment. You are setting up your experiment, connecting wires, putting different things through mixers and amplifiers and making sure everything's working correctly. We do spend a bit of time sitting in front of computers. We will in superconducting circuits in particular come up with the idea for a qubit. We'll do a bit of coding, write its Hamiltonian, figure out what its wave functions are going to look like, what its energy spectrum will look like, whether it will behave well, and do what we want. And then we have a shot at designing it. We do some simulations of the design. We take it into, I don't know if any of you have seen the yellow rooms in the SNH. Have people seen those? So if you go to the research area of the SNH, which is just the building behind this building, there are big yellow glass windows where you'll see a lot of kind of high-tech instrumentation and people walking around covered head to toe in white suits. The reason for that is that that's where we fabricate nanoscale quantum circuits. And so all the air in there is heavily, heavily filtered, basically removing dust. We wear the suits so that dust from our bodies doesn't get into the clean room and contaminate the devices that we're trying to make. So we make our devices in there, we come out, we load them into our fridge, we measure them, and we kind of repeat the cycle. So one of the things I don't have a huge attention span for any one thing. And so one of the things that I really like about experimental physics, in particular, I don't know if this is the case for all experimental physics, but the type I do is really varied. In a 2-month window, you get to often do all of those things that I just mentioned. And so that's what my, when I'm in the lab working, what my day-to-day looks like.
That's actually a part that does sound like the films with the hazmat.
Well, I guess some of the similarities, I also like listening to, I guess, sick beats and coding or doing theory. So I guess, yeah, that's a similarity with astronomy. But yeah, I guess that is the day-to-day of a theoretical physicist, like doing your, if it's pen and paper theory, doing that. And then spending most of the time thinking like, why aren't the equations the way I think they should be? Are they wrong, or am I not understanding them correctly? Drinking a lot of tea and thinking why it's not working. Yeah, now I do a bit less of that because I have a few students, and so I have to work out why their equations aren't or why I don't understand what's going on when they do. But yeah, I guess it's yeah, that's what the daily life is. Chatting with people as well is very very good to get things fixed that are not working.
Cool. Now I will jump back to that question that I mentioned before. Tell us about your great aspects. So it's something that on a day that you are tired, when you think that's actually the reason I'm doing physics and I like it. And sometimes the reasons that a lot of people don't see, all the things that are perhaps a bit negative on the aspect, something that, again, the public doesn't see about research. Potentially for me right now as an undergraduate student, it's a lot of imposter syndrome. For me, I feel like there is a lot of people who are smart around me and I don't know if I'm performing as well, right? So how does that look like in research? Is there something similar to that? And what are the other aspects?
Yeah, that depends on your personality, but it doesn't get better. At least for me, yeah, I still have imposter syndrome. I guess the thing that you really look forward to in research is when you finally understand what's going on. Yeah, or why something doesn't work or why it works. Yeah, I think when once you fully get it, that's a great feeling.
Cool. Yeah.
So earlier this afternoon, I was comparing research to skydiving. I was talking with somebody about one person that we know of, not personally, who's a researcher who doesn't have or doesn't appear to have imposter syndrome. And I was comparing that how to when I did skydiving, the instructor who was going to be taped to my back as I jumped out of a perfectly good plane said to me on the ground, "Are you scared?" And I said, "Yeah, a little bit." And he said, "Good." Because people who aren't scared tend to do silly things. And I think that imposter syndrome keeps us honest. It is unfortunate that it's there sometimes a little bit more than we need, but it will always be there. And I think it's really, it can be used as a good tool. I mean, you probably know a lot about the idea of doing sanity checks, right? You want to make sure the numbers work. You test out basic things that you know the answer to make sure that everything makes sense. And I think those moments when something isn't working and you can kind of question it and use basic sanity checks to figure it out, you're like, oh, this code isn't working. Who wrote this dumb code? And you're like, oh, wait, it was me 3 months ago. And then when you figure out, this is why it's not working, totally agree. That's what makes it good. That's what makes it, those are kind of these like small nuggets of light when you either figure out why something isn't working or you figure out why something works the way that it does on a deeper level. You know, when I was studying this object that was giving off these weird pulses in radio every 2 hours, and when you figure out that it's tied to the rotation period of the star and you can understand, holy crap, these radio pulses that I'm getting are the star, you know, hundreds of thousands of millions of kilometers away, just turning around. There's something really, I don't know, really, really nice about that.
Oh yeah, that feeling where you know I've seen something that literally no one else in the universe has ever seen. I have to say the best bit of this job really is being at a telescope. Got the whole telescope to yourself. You go out, look up at the night sky, and you just sort of go, yeah, this is why I became an astronomer. This is why actually it's quite unfortunate that now as astronomy becomes more, well, it goes into its next phase, there is less and less opportunity to actually do this and do the hands-on observing. Nowadays, astronomy, you know, it's all these giant telescopes and, you know, data is taken for you and pre-processed and you never get to actually do the going to the telescope. That's a pity because that's where the romance of the whole thing is. And I like it. Yeah. It does make up for the bad bits in between, but yeah.
I will actually throw in another topic as well, which I am pretty sure it will be shared between both sides. And it is sending a paper to be published and having it critiqued. How does that process feel like? Like when you know someone else will be reading a paper, trying to specifically pick out mistakes in it and see how it feels like.
Well, again, imposter syndrome helps here because it just means you do the best possible job you can before you submit it, rather than just dashing something off and letting someone else tear it apart. I've only ever received one really bad referee's report, where the referee basically, no, two, there were two. One, I'd made a terrible, stupid mistake that I hadn't known about and was very grateful the referee had picked me out on it. But it's like, I really did feel like going and putting the covers over my head for a while because it's like, oh God, it's out there that I did this terrible thing. And the other one, yeah, referee came back and said, look, you just haven't understood what you're talking about here. And it's like, I tried. Anyway, the thing is, it made a better paper in the end. And so, yeah, you just have to kind of put up with it. Again, being honest with yourself and saying, yep, fuck that one up big time is the thing that helps you get through. It doesn't feel good at the time, but yeah, it's part of the process. And as I say, I do look back and say, you know, most of my papers, the referees' reports were pretty good. So I'll take an average.
Can I tell a story about the first paper that I
Absolutely.
So, it was early in my PhD. I'd done honors in the same lab, so I had an advantage, and we submitted a paper. I had no experience of science. I didn't really know. No one had told me what the process was like, so everything was new to me. And so we submitted this paper, and David, my supervisor, got the referee reports back and forwarded them on to me. I was downstairs in the lab, and I got these reports, and I was devastated. I was sitting there on the brink of tears, pondering quitting my career in and David comes downstairs and comes into the lab, and he's like, "Did you see the referee reports? They're great." Send me the wrong ones. Like, I don't understand. I think that like after you see enough referee reports, you kind of realize that, like, you know, they will always be a little bit critical. And then you write referee, you get papers to review yourself, and you also critique other scientists in their work. And I think for the most part, you either get mad at them and disagree with them and get ragey, or you kind of, you assume good faith and that they're there to help you do better science and to point out things that you might have missed or ways that you could make the paper better. Yeah, I think referee reports, if you're not used to reading them, rarely will you get them and they will all just be glowing praise about how brilliant you are. They will probably have some sharp criticism in there somewhere over something in the paper.
So I guess sincere criticism is valuable in a referee report, I guess. So I agree with some of the points that were made. Yeah, of course, it's super annoying when they didn't put in the effort to try to understand the paper. And then they still have strong opinions. That can be pretty annoying. Those are the kind of the worst ones.
Sure. I guess this one kind of goes towards a more theoretical part of the aspect, but that's a question that was sent to us from one of the audience. It was that, do you ever reach a point where you realize the topic of research has turned out to be so abstract or so theoretical that it can't possibly have any practical use to anybody? Does such a point exist in physics research? How do you know when you reach it, and what do you do when you get there?
Like we've all been down Wikipedia holes, right? And you're just like opening up more and more tabs. And you kind of do the same thing when you're looking for a very niche research topic or like a part. It's basically like you'll spend 3 days reading papers to write one sentence. And when you realize that you've gone more than half a century back in the literature and you've crossed into a different field, that's the stop. I had the pleasure of finding myself in the geophysics literature when I was trying to understand this one mechanism that when I started, I was like, oh, okay, this is how brown dwarfs give off radio emission. And then I noticed that every paper was just citing the mechanism on kind of a superficial level and then referring to the previous paper. And you just kind of follow that chain all the way back until you realize, wow, this is science. I mean, like you were saying in the beginning, these are open questions, and we can get to a point where there's kind of an accepted truth that's generally understood to be the main answer, but this is kind of why we do what we do, right? You'll hit a certain point half a century ago, and that's it,
That's actually a really good point. Everyone should do this at least once. Try to track back where a particular process or equation or, whatever fact in your field comes from, because it's really, really scary sometimes when you, as you say, someone cites this paper, so you go and read that paper, but they didn't do it. They cite another paper, so you go back and read that one, and you go back 37 years and you find it was some terrified undergraduate who wrote a paper that has been cited without comment ever since. And it's sort of like, really? That's the best we can do? And you say to yourself, well, I guess it can't be very wrong or someone would have noticed by now. But, every now and then it's very interesting to work out that that's how science is done, if you know what I mean. That, yes, you too can be writing a paper that will just go down into law. Sorry, that's slightly off the topic. I have to say, as an astronomer, can I say that I have never been under the delusion that anything I do has any relevance whatsoever. Sorry. I like to talk about the big picture, origins and understanding our place in the cosmos. It's the best I can do. Sorry. every time an astronomer has to write why your field is relevant in a grant application, we kind of go, oh dear. so yeah, sorry, I can't answer that one.
I will just say I'm an experimentalist, so I can't necessarily comment. But what I do think is a skill, and I really admire people who are good at it, is knowing when an avenue of research that you may have invested a lot of time and energy into is not worth pursuing. I think that often just by nature of having tried something for a really long time, there's the tendency to just want to keep trying until you get something. And so I think it's for many reasons, often a really helpful skill to be able to not take science too personally, and you know, acknowledge that something could have been a good idea, and then you tried it and you learned more and you learned that it didn't work. So you're not going to do that. And having, I think, the wisdom and sometimes courage to let an idea go that isn't going anywhere is also a really important skill to have as a scientist.
Yeah, I feel like that's something you see even when you start studying as an undergraduate and you get stuck on that one tutorial question and you never know what you found. Cool. I think Kavi mentioned this earlier, so we definitely get onto that as well. A lot of people study maths and physics here, but that doesn't necessarily mean that's the case for everyone, obviously. So I want to know, what are obviously the fundamentals of physics is written by mathematics, and everything that you basically use every day is written by it. What are some specific parts of maths or units that you think are necessary to pursue when doing physics, and what is it that's not necessary? I think you said you had an experience that wasn't quite pleasant. So if you want to mention that for us.
Yeah, I mean, what I was saying before we started was, especially for me as somebody who didn't have a strong math and science background, I was like, what's the point of this? Like, why am I doing all of this math without necessarily seeing an application? I think the kind of general vague hand-wavy answer I could give is that, I mean, most math is going to be relevant to some part of physics. And I think what's really maybe the best advice I could give, rather than saying specifically what was good for me, is like, do a project and figure out what you need for that project. And I think that will really motivate your understanding of a particular mathematical topic. So like for me, I think it was the end of first semester or at some point during first year undergrad, doing Fourier transforms, it meant nothing to me. Like, why do I care? But as a radio astronomer, it's everything, right? Like you're using Fourier transforms for literally everything. And I think that if, I mean, it's hard to rearrange syllabuses and the way that degrees are taught, and obviously that varies from, you know, university to university. But you yourselves, if you can find a project that interests you, and then just really try to get a good understanding of the math that's necessary for that, is probably the best way to make math actually useful and relevant.
Yeah, this feeds into something that I've thought for a long time, which is that the most important skill you can take from a university education is learn a bunch of stuff, accept that you're going to forget it, but know that you can learn it again. Seriously, that is the point. The thing is, the likelihood you will remember your thermodynamics in 10 years' time is, can I say, approaching zero, you know, asymptotically. But if you need it, you know in the depths of your heart that you once knew thermodynamics, and therefore you can know it again. And I think the same is true for maths. It's like, quite frankly, it doesn't matter that it gets a little fuzzy after a while. You know you can do it. Again, can I just tell another story? The same guy who told me about the 10-set plastic ruler came to me one day while I was doing this project and said, I have been working over this integral and I cannot do it. Can you just give me a hand? And so he gave it to me. It was this simple integration by parts. And so I did it and I gave it back to him, and I must have had this look on my face. Said, you just wait. One day you won't be able to do it either. I hate to say it, but he was so right. so yeah, but don't worry about it. If you ever need to know integration by parts, you can learn it again. Okay, so take that from now. Like everything you learn now, it's going into you the same way the potatoes you eat become part of you. Okay, the potatoes themselves aren't there anymore, but you can redo the potato. No, sorry, that's not what you do. Sorry. Anyway, yeah, you can learn it once, you can learn it again. That's all that matters.
What was the question?
Potato. Yeah, perhaps what part of mathematics that you learned early on do you think you are using now at the moment?
Probably linear algebra. That's the most useful one.
Statistics. I wish I'd done more statistics.
Statistics too.
So if that's it, and I will want to go right to the. Oh yeah, for sure, absolutely.
Okay.
Absolutely.
Of course, I didn't do. But if you love quantum mechanics, and it's not to say, I would also say, as well as learning things that you didn't know, you can also pick up things as you go along. Also, as well as remembering things that you did once know. So I was too busy pursuing law to do a lot of linear algebra, but I also didn't do Hamiltonian and Lagrangians. And as a quantum physicist, they came back to bite me. And so I learnt them on the fly, which you can do, but I still wish I had have done that course when I was at university.
Yeah.
One
So
thing I mean, Xanthi was talking before about resilience, and I think that if you're resilient and you know how to recognize a learning style that suits you, right? Because you've all encountered topics that make zero sense to you, and yet somehow you learn how to, wrap your head around them. And if you can just repeat that process every time something new comes up. So if you're like, oh, I need to learn Hamiltonian dynamics, how do I do that? And then you just say, okay, I have to be resilient for a little while. I have to remember, like, what's the process that works for me, whether it's, read the Wikipedia page, get a basic understanding of what the heck's going on, watch a YouTube video, do some practice problems, and then dive into a textbook, figure out that process. And just, every time you're faced with something new, whether it's a fuzzy topic from the past or something totally new, just run through those steps.
And some people prepare to get, go through the whole theoretical thing and understand something in the theoretical way before, actually trying it in their data. Other people have no idea when faced with the theory and just want to dive right in. Yeah, when I was learning Fourier transforms to study radio astronomy, as you say, why do I care about this? But as soon as it's like, a UV plane, I see. And that becomes, you turn that inside out and it becomes an image. Now I can go back and understand what we were doing. You can learn that that's the way you learn. And once you know that, then it means don't bother studying the textbook before you get the data. Just dive right into the data and do the theory alongside, or vice versa, if that's the way you work.
Cool. So I feel like for next stage, I'll let the audience ask questions as well. So I'll probably keep this mic around here, and I'll probably move around if anyone has a question to be asked.
All at once, please.
Yeah, for sure. Just keep on. I'll come along too, so you can hear it as well. I'll just take this one. I think that'll be easy. Yeah.
Lapel mic. Okay. So my question is, how do you know if the thing that you should be doing with your life is research in physics? Or how do you know if, like, not you specifically, but like, say me or probably a lot of people in this room are trying to decide, how do you know if I should decide to do research or if I should decide to go off and go to a company or something? How do you work that out? Maybe how did you guys work that out?
I feel that my entire career was a case of falling in, as illustrated by the earlier anecdotes, and it worked. Sorry. I think you can't know, you can only do it. What I would say is live in the moment while you're doing it. It's like part of the problem that you people have, and I know you know it probably a lot better than we do, is that the future for, being able to say, I want to become a scientist and being able to do it, the pathways are closing. You know what I mean? We are training far more people than are ever going to get jobs being astronomers or quantum physicists or whatever. And so, even if every single one of you say you would like to become a researcher in physics, the likelihood is you probably can't. And so some of you will be ending up in something else. And all I can say is try and live where you are now. It's like if you do a PhD, you're an astronomer for that 5 years or 4 or 5 years. Do you know what I mean? And you should make the most of it and say, this is what I'm doing, even if you don't end up getting the faculty position, being able to do it for the rest of your life. Does that kind of make sense? There isn't only one version of you. There isn't only the version of you that becomes a researcher. Do you know what I mean? There's also the version of you that takes the skills you learn as a researcher and goes and does something else. And, in the many universes theory, both of those are perfectly fine people. Do you know what I mean? And so, again, don't tie everything to a hope that may or may not happen. All I can say is give it a go,
Yeah, I was just going to say the thing that you added at the end is exactly it. Like the skills that you would pick up along the way. I mean, the short answer is to your question, you got to try, right? Do a project, see how that suits you. When I started my honors, I was in this weird position where I thought I wanted to be a researcher, and people kept saying to me, so what, you're just going to stay in academia forever? And I wanted to say yes, but I was also like, well, I don't know what it's like to be in academia. So the only way to figure it out is to try. And I guess, yeah, the real key point here is that you stand to gain so many skills that you can take with you afterwards if it doesn't work out. If you find that it isn't something that suits you, or if you realize that there isn't a position available for you. I mean, basically, anybody who gets a PhD in physics can walk into most high-tech jobs doing data science related things. I mean, just being a physicist working in a high-tech company is something that is a very desirable skill. And like, you know, if you decide that you want to work in finance, like people in finance love physicists for some reason. So yeah, the skills will be useful to you regardless of whether or not it suits you and whether or not you manage to make a career out of it.
Amazing. Any other questions? Cool. Yes. Yes, absolutely. Sorry.
It's not that important.
No, of course, sorry.
That I think is true of decision making is often it can feel like a lot of pressure if you have 2 options or 3 or 4 options, and you feel like you've got to make the right one, and you possibly fear regretting your choice if you make the wrong one. I happen to think that often when we are confronted with multiple choices, we could be very happy choosing any or all of the choices. And I think that, like, you know I could have enjoyed being a lawyer and probably really would have loved that career. I don't think like, yes, physics was definitely the right choice for me. I love being a physicist and I really enjoy my job, but I think that it's not like, there's not only one path to happiness and you must find that one path. Otherwise you'll be stuck in unhappiness.
This question's for Sahand. Having done like the optics course last semester, and you said like one of the most important fields of math that you use would be like linear algebra, and we saw a lot of that in that course. What does it look like what does it look like at the level you're at now with like in research? Like what does the linear algebra look like?
Oh, yeah, what does it look like? Well, in quantum mechanics, the overarching theory, it's kind of a linear theory. So Schrodinger's equation is linear. So linear algebra is everywhere there. So that I don't know. On the day-to-day, like, am I pen and paper calculating the eigenvalues 10 by 10 matrices? No, I don't ever do that. But yeah, in quantum physics, there's linear algebra everywhere. I don't know how to be. Yeah, at this moment, I don't know how to be more specific. There's linear algebra in machine learning everywhere as well. Yeah, you don't have to diagonalize large matrices, but you have to know what you're doing and write ideas in terms of linear algebra and use the properties of linear algebra. Yeah.
What do you think your fields would look like in like 10 or 20 years time from now? All of you.
Will we have quantum computers? And
That's what I feel like there's an ongoing joke that people have been saying we'll have a quantum computer in 10 years for like the last 30 years or something like that. I don't want to join the I think there are a lot of really big challenges in quantum computing. I think that this is a very wishy-washy answer. I think, there's a lot to be said about incremental progress, and, slowly working to understand materials issues and like slowly chipping away at it. Occasionally an idea comes along that really like accelerates the field. I think quantum computing has a lot of big challenges to overcome. I think potentially there could be some really different types of qubits in 10 years that people are looking at that we don't currently have or know how to build, which I think is really exciting, hopefully with a lot lower error rates. Big companies have their roadmaps where, in the next 5 years, they're going to have a few thousand qubits on a chip, which is really exciting. That probably won't be happening in university labs. University labs tend to do research at the fewer qubit level that can kind of feed into those bigger quantum processes. I don't want to promise we'll have like a fully functional quantum computer in 10 years, lest I become one of the many who have said that.
Yeah, I just want to maybe add a bit of a comment on that. So, the size and the quality of quantum, so the number of qubits and the error rates. So the number of qubits is going up and the error rates is going down. And the interesting question is like, once the quantum computer is sufficiently large, how large does it have to be for us to be able to do something useful? And because at the moment, researchers don't know what's a useful calculation that we can perform on a quantum computer that can't be done faster on a regular computer. So in 10 or 20 years, I think once the quantum processes get bigger and bigger and faster, that's, I think, the important question to answer. So that's an outstanding research question. You could kind of hear sometimes in the news that quantum computers are going to do all of this stuff and they're going to be so much faster than regular computers. But at the moment, if you get a quantum computer with around 10,000 qubits, even with very low error rates, it's not clear what that can do that a supercomputer can't do. And supercomputers are getting faster as well. NVIDIA, they recently released a processor that's 2 or 3 times faster than their previous graphics card. So, yeah, we have our work cut out for us.
Maybe if we could extend a bit on that question, is that when you do your work every day, is that something that you particularly keep in mind? Maybe what you think the direction of the field is going to be ahead of you? Or do you basically live in the present and do what the tasks that you have at hand?
Mostly the latter, I think. But can I just say, by the way, that in astronomy, for 30 years, gravitational wave astronomy was 10 years away. And they made it. So it can happen. I think I've already answered the question about where I think astronomy will be. It's all going to be about big data, which means that you guys who want to get into astronomy should be thinking computers and computational methods, because that's going to be the thing. There's going to be this fire hydrant of data coming at we're going to have the orbits of 1 billion stars coming from Gaia. We're going to have the positions and colors and magnitudes of every object in the sky, night after night after night. The problem that astronomy is going to have to solve is how to sift through that data and find the interesting stuff. So yeah, that's going to be the challenge.
Maybe just to give you an idea of exactly how challenging that will be, Helen mentioned supernova 1987A before, which was the first supernova discovered in 1987, right? So supernovae then were basically just a year and a letter. And now supernovae are a year and 2 or 3 letters. There are that many supernovae being found. And one upcoming fire hose of data that we're going to have is the LSST. So the Vera Rubin Observatory in Chile is going to be observing an expected 10 million transient astronomical events per night over 10 years. So yeah, we cannot emphasize enough the importance of data. I think to your question about how relevant, how much I think about that question and dread it existentially on a daily basis, I generally look at data, because I don't have a data science background. But, you know, naturally it's a big part of my life and is obviously always becoming a bigger and bigger part as I deal with more of this big data, which is really, as Helen said, the future of astronomy. Generally, I think if you're going to do something more than a handful of times, you should look to see if you can automate it, if you can write a Python script that does it, or get ChatGPT to help you write it.
Inevitably.
Yeah. But the physicists are important at the end of the day, because if you're talking about classifiers, you have to understand the physics to understand what you're asking the computer program to do for you.
Mm.
Caveat.
Next question.
I'm just wondering, like, how far or close the field of physics and astrophysics and quantum is to like the media, because the media seems to overpromise a lot of things in terms of technology, and they love to do this because of investors and to say we're going to have like graphene phones in like 5 years and all this crazy stuff. I'm just wondering like where that is in regards to your research and work, and where the media is kind of like how big is this gap? You know, is the media talking like 30 years ahead, or is it 20 or 10 years for a quantum computer? You know, so.
I think you just need to be careful about what you define as media. Look at sources like The Conversation, look at articles that are written by people who are doing the research rather than things, I hate to use this phrase, but from the mainstream media, because they tend to get contorted for the sake of clicks. The media advisor in the, does Marcus do outside of the School of Physics, or just physics? Faculty of Science, yes. Yeah, so the media advisor for the Faculty of Science, Marcus Strom, has a list of forbidden words. But when you're doing a press release, like don't say breakthrough or groundbreaking or things like that, because they will tend to mislead the reader, and they will also tend to mislead the journos who are well intentioned. But when they see certain words in the press release from the university, they will think those words have different meanings to what the physicists think they have. So yeah, I would recommend to try to get as close to the source as possible when you're trying to get a better understanding of how far away these things are, you know, on any given topic. And I would also recommend that for those of you who do go into research, it's part of your job to communicate the science that you're doing in an accurate way, making it interesting without making it clickbaity, you know, more than necessary.
Get into the habit now of clicking through and reading the Nature paper or whatever when they have a press release. It's you know, you don't understand most of the paper, but that's okay. Most working physicists don't understand most of the paper. When you're reading a paper, you read the abstract, you look at the graphs, and you read the conclusion. And if you haven't understood what they did from doing that, the paper was badly written, quite frankly. So anyhow, the point is you can start now, and that will give you the tools you need.
Yeah, I think you said it very well. I think that very well-intentioned journalists, you know, just kind of have a different calibration of what certain words mean. And you might talk about a breakthrough, and maybe it's a breakthrough for your subfield of a class of physics that, you know, maybe 10 people in the world are working on. And it is exciting, but it's not necessarily like the world shattering. And so I think, yeah, I think it is important to kind of read sources that are closer to the actual source of the research.
Yeah, I think I agree with what's been said. Yeah, these articles all exaggerate. That's the conclusion, I think.
Any other questions? Yeah.
What are some future collaborations you guys think? Like, I mean, if a quantum computer was made, how would that affect astrophysics, do you think?
Need to factorize large numbers.
One of the things that came out of this conference that I was at, a workshop that I mentioned I was at a few weeks ago, was a collaboration between me and somebody who works in machine learning. And one of the things we're trying to do is see if we can recognize astronomical sources using machine learning rather than traditional methods. And at a certain point, and we're pretty much there, the comparison of how efficient that process is just comes down to computing power. And, you know, the first test I'll do is to benchmark how long it takes me to do this with this new method, but the new method is getting faster and faster as the computation is improved, and hopefully that will be one of the uses that we find for quantum computing.
This isn't exactly a question, but this is more how do people who are trying to build quantum computers steal from everybody else in terms of and the answer is a lot. We steal from the way radios work. We steal from work that chemists have done for a long time studying oxides and surface chemistry. Who else do we steal from? We steal from quite, the knowledge and the solutions to the problems that we need often come from quite different fields to what you might intuitively expect for a physicist staring at some nanoscale thing. So I would say that in the meantime, before we make a quantum computer that can benefit everybody else, we benefit a lot from other fields in terms of the things that they've learned.
Any other questions?
I was just going to ask how the data is actually stored. Like if there's that massive influx, is there a worry that could come before the quantum computer is built and then it's only in a specific mega computer somewhere? Is there a worry that there wouldn't be would there be several places to store it?
Yeah, so with that specific example of the LSST, there are 3, maybe 4 data servers around the globe and a network of fiber optics cables. The LSST has been on the horizon for, I think they've been planning it for about 20 years. And they're expecting first photons at the end of next year, which means first science data start the year after that. And a lot of that time has been figuring out these engineering questions and data science questions. So yeah, that specific problem has been solved, and it's part of a global collaboration of people working together and agreeing to front the costs for the data centers and that sort of stuff.
It is now a major part of the cost of a big observatory is how do you deal with the data? So the square kilometre array in Western Australia, for instance, has its own supercomputer centre set up with, massive broadband connections to the site so that this torrent of data can be taken somewhere. Yeah. And as it is, they cannot actually store all the actual information taken by the telescopes. They have to throw out the raw data and only store sort of intermediate data products because there's just too much.
Yeah, I mean, your resolution, well, specifically your time resolution with radio telescopes is not limited by a technological thing of, how good can we get our machines? It's how can we store this? So there are programs that look for very fast radio bursts that occur on sub-microsecond levels, and they're basically you're not saving that time resolution of data. It's not possible. We don't have the storage capacity. And so they're basically doing the analysis live as part of the observation pipeline and checking and dumping. So that data's gone if they don't find anything.
Any other questions? There was a question that when we were talking beforehand that I came up with, and I think you kind of mentioned it as well, Kovi, about what you decide to put out for media to see and for people outside of the scientific community to see. What do you personally think are some of the responsibilities you have as a scientist for yourself, for your community, and perhaps for the audience outside and the world?
I think that your responsibility should be to try to excite other people in the way that you're excited about your field. Your responsibility should be to help platform other scientists who work in different fields or who come from different backgrounds who maybe don't get the same exposure that your research is getting. And I think that you should do that in a way that walks this very fine line of kind of explaining the way that you would explain to a mate at a pub or a family member, not trying to over-explain and getting stuck in the I mean, you should be able to understand your audience, choose a platform that works for you. So I do science communication on social media, and I also do science communication in, written articles for Space Australia and for The Conversation. They're very different. And so the amount of depth and detail that I can go into and how scientifically rigorous I can be changes depending on the platform and the audience. But at the same time, you always have to just like not talk bullshit. Don't overhype your science. That's the worst thing you can do, because it's kind of like a boy who cried wolf situation. So if you say something that isn't accurate and you get called out on it, it's harder for you to be believed the next time. I think that scientists who do that, who make grand statements that aren't necessarily connected to reality, let's say, are doing a disservice to the entire community.
Any input?
Hope that wasn't too strong.
No, I agree. Yeah.
Cool. Perfect. I think in that case, we'll wrap it up. Thanks so much for being with us here today, having some cool discussion. And thanks to the audience for being here as well. So if we get another round of applause.